we will continue our discussion of kinematics of a particle, and in particular what we are studying is when a particle is moving in a straight line. In the last class, we had seen the definition of displacement, path length and distance. Now, today we start with a graphical description of displacement versus time for a particle which is moving in a straight line. So, let us say a particle is at a particular location. So, this is x on the y axis, time is on the x axis. If a particle is at rest, then it will be at the same location. So, a straight line which is parallel to the t axis, this represents a particle at rest, because as time increases the displacement is not changing. So, therefore, the particle is at rest. Now, we could have a second case where the particle starts from the origin, and as time increases, the particle keeps on increasing its displacement. So, that means it is moving along a straight line and the x value keeps on increasing. And if it is moving, if this x t curve, if this is a straight line, this represents that the particle is moving equal distance in equal interval of time. So, and this motion is said to be a state of uniform motion, which means the particle is travelling at a rate which is constant. We could have more complex motion. For example, we look at a case of a car which is starting. So, motion could be more complex. Let us look at a car which starts from rest and it starts to move then it moves in uniform motion. Then after some time a brake is applied and it comes to rest. So, if we generally would like to plot x t curve for this type of motion, then what we will find is at time t is equal to 0, the car is at rest. Then it starts to increase its displacement, and after some time it comes to a state of uniform motion and it continues to move with uniform motion, and at this time let us say a brake is applied. If a brake is applied, the car will move slowly now as compared to the previous state and eventually comes to rest, but its x component will keep on increasing. So, when we apply a brake here, what we find is the car slows down, but it continues to move ahead. After some time when it is at rest, then the x component or the displacement will not change with time, and this is how the x t curve for a car which is starting and then moves on along uniform motion and then when it has come to rest looks like this. For a particle which is travelling, let us say from O to P with some uniform motion and comes back from P to O, how will the x t curve for this motion look like? Here you will realize, well, the particle initially goes from, this represents the state O, it goes from O to P, and after P now what we realize is that x starts to decrease. That means the particle will now start to come back, and when it comes back to O, x has again become O. So, this represents a particle which is moving forward, and then because the x values start to decrease, we see in the curve it starts to come down. So, this is another of the xt curves. Now, what we see here, a critical component in these description becomes how fast is the position changing with time. And this we describe with terms called speed, and if we include the directional aspect of speed, then we get what we call as the velocity. And we will now look at the precise definition of speed and velocity. First, we define a term called average velocity. And average velocity, this is equal to change in displacement divided by change in time. What this means is that if the displacement over a time interval delta t is equal to delta x, then average velocity will be equal to the change in displacement divided by the time interval, which is delta t. So, delta x upon delta t is equal to average velocity. For average velocity, we use a symbol v with an over bar, and this is equal to change in displacement. I can write it as x2 minus x1. Change in time can be written as t2 minus t1. So, this is what the definition of average velocity is. Now, if we look at the units of average velocity, the units of average velocity, they will be length units divided by time units. So, that means we can write the units as L over T, which in SI units will be meters per second. Other common unit which we have, another unit which we talk of when we talk of speeds and velocities are kilometer per hour, particularly when we talk of vehicle or aeroplane moving, then we could list them in kilometers per hour. One thing which all of you should realize, that when you solve a problem and if data is given in different units, then we should make the units uniform and then solve the problem. You can't add kilometers to meters. You can add kilometers to kilometers or meters to meters. Now, let us see the graphical meaning of average velocity. Well, let us look at some aspects of average velocity. Average velocity, we realize first of all, this is a vector quantity. A vector quantity means that it has its velocity, it has a direction as well as a magnitude. But when we look at motion along a straight line, the direction is given by the sign of displacement, and we do not require any other thing to explain the direction. So, direction is given by the sign, and this could be either positive or negative. If it is positive, that means we are moving along what we have called as the positive x axis. If it is negative, then we are moving along negative x axis. So, This gives us the sense of direction. Now let us see in a graphical sense, if we have the xt curve and this xt curve is given like this. Now let us say this is the interval, time interval t1, and the particle is at point P and the particle is at point Q at t2. Now the displacement here at Q, let this be x2, and the displacement at P, let this be x1. So if we look at the average velocity during this interval from t1 to t2. So let delta t be equal to t2 minus t1. The average velocity will be equal to, in this interval, will be equal to x2 minus x1 divided by t2 minus t1. On this graph, if we look at it, this is x2, so x2 minus x1 divided by t2 minus t1. Now this will be nothing but, if we make a straight line PQ, then slope of this line, slope of the line PQ will be equal to the distance along y axis, which is delta x, and the distance along x axis, which is delta t. So slope of the line PQ gives us the average velocity. Irrespective of the shape of the xt curve, the average velocity will be given by the slope of the straight line. Now average velocity v bar can be positive, it can be negative, or it could be 0. If we have xt curve like this for uniform motion, this is a case where v bar is positive. And this we can also see by slope of the curve. If the angle which the xt curve makes with the x axis, if this angle is acute, then the slope is positive, and here v bar is positive. If the xt curve looks like this, here the average velocity v bar is negative. And again we can have a look at this with the slope of the curve. Slope of the curve is the slope which this line makes with the x axis here, and here we will realize when we make this straight line, the angle theta which it makes with the positive t axis here, this is obtuse, it is more than 90 degrees. So this represents negative slope, and therefore here the average velocity will be negative. And if a particle is at rest, it is not changing its displacement. So this is the xt curve. This represents 0 average velocity because the particle is not moving at all. Now what we have said is that this velocity v bar, when we define the average velocity, this involves displacement. So that means we are looking at the net value of x, x2 minus x1. Whereas when we talk of the concept of average speed, then what we do is we look at the total path length travelled divided by the time interval. So when we calculate the average speed, it tells, we count the total length of the path moved, not displacement, and that is what gives us the average speed. Now one thing we will realize is that average speed has the same units as average velocity. That means the speed units will be, again they will be length over time, and in SI units this will be meters per second. But the magnitude may not be equal, because path length is always greater than or equal to displacement. And therefore the average speed which we will get, average speed will always be greater than or equal to the average velocity. And the reason why this happens is that because if you return on a path, then the displacement will reduce, whereas the distance does not reduce, path length does not reduce. So, average speed is goes like this. Now, while we talk of average speed, the concept which is more useful when we talk of our description of motion along a point is the concept of instantaneous velocity and instantaneous speed. And what do we mean by instantaneous velocity? Instantaneous velocity, as the name suggests, is velocity at a particular instant. So, how we define this is, if we take the displacement delta x divided by delta t, this is how we will get the average velocity. Now, if we make our time interval over which we are observing the change, we make it smaller and smaller, and when we make it smaller and smaller, eventually we say when this delta t approaches 0. So, we say this is the limit delta t going to 0, then this quantity which we get, this is what we will call as v, or this is called the instantaneous velocity. So, instantaneous velocity is the average velocity in the limit that the time interval over which you are considering this average is becoming smaller and smaller, and this what we say is the rate of change of position with respect to time. Geometrically, let us try to see how this looks like if we look at the graph. So, geometrically, when we see if this is the xt graph, now we are, let us say we want to calculate the instantaneous velocity at t is equal to t1. So, then what we will look at is we focus at t is equal to t1, and then we take the displacement at a small distance away from t1. We could either go in the plus direction or in the minus direction, it does not matter, but eventually then what we will do is we will take the limit of this gap in time approaching 0. So, when the gap in time approaches 0, what you will realize is that this will, the delta x by delta t will approach, this will approach the tangent or the slope tangent to the curve, to the xt curve at t1 if delta t approaches 0. So, therefore, what we have is that the slope of the xt curve or tangent to the xt curve gives us the instantaneous velocity. So, tangent or slope of xt curve at t is equal to t1 gives the velocity, or now in fact when we once we have defined instantaneous velocity in later discourses, we will remove the word instantaneous. So, that is why that is called the velocity at t is equal to t1. Now, here you will realize if we take the magnitude of instantaneous velocity, this is what we call as the instantaneous speed. And in this case, when we talk of instantaneous velocity and instantaneous speed, the magnitude of the velocity will be equal to speed, which may not be the case for average velocity and average speed. But for instantaneous velocity and instantaneous speed, this is how we will have. So, therefore, graphically if we have to look at it, then if we have the xt curve and the slope of the xt curve will give us the velocity. So, the magnitude of instantaneous velocity is defined as instantaneous speed. And here we will realize that the two magnitudes are equal, whereas when we talk of average velocity and average speed, the magnitudes may not be equal, because we are looking at the motion only over a very small interval delta t around t. So, therefore, these two magnitudes have to be the same. It is just that the instantaneous velocity for 1D motion can be negative, whereas instantaneous speed is always positive. And one practical application of this is if we look at when we observe the motion of a speedometer in a car, then what the reading which we get is the reading of instantaneous speed, which as the car moves at each instant, the speedometer gives us the speed of the car at that instant. Now, let us revisit our example of the particle of a car which had started and which was moving, and which so we had seen this case of a car which started from rest, it increased its speed, then it went into into this motion of uniform speed, then brakes were applied to it, and then it stopped. So, now here if I on the same curve, if I plot the value of the instantaneous velocity, so then what we will find is that in this period when the car's speed is increasing, the instantaneous velocity will take a shape like this, that it starts from rest, the velocity keeps on increasing. Then in this period when we have uniform motion, the velocity stays constant. So, the velocity is going to be like this, that means it is constant at some value. And then when brakes are applied, in this period the velocity starts to go down, and finally when it comes to rest, at that time the velocity will go to 0. And if this is at a uniform rate, if this velocity is changing, what we get is it starts to reduce, it comes to 0, and then once the car is at rest, the velocity goes to 0. So, this is how the velocity time curve looks like for the car at which was started to move. Now, the next thing what we do is we have velocity, but as we have seen in this example, velocity could also change with time, it need not always be constant. So, therefore, we define to account for how the velocity is changing, rate of change of velocity. So, therefore, then we have velocity may not be constant, and actually as we see, velocity could either change as a function of time or as a function of distance, and maybe even or both. But what we do is we define the rate of change of velocity with time, and this is what we call as acceleration. So, acceleration denotes how fast the velocity is changing with time. And again in acceleration, so we use the symbol A for this, and we can define two quantities. We can define average acceleration over a time interval delta t, which is equal to t2 minus t1, and this average acceleration will be equal to v2 minus v1 divided by t2 minus t1, and this one can write it as delta v over delta t, where v2 is the instantaneous velocity at 2 and v1 is the instantaneous velocity at 1. So, this is how we define average acceleration. This also is a vector quantity, it is a difference of velocities, and the symbol we may use for average acceleration is, again we use bars for averages. So, this is a bar. And if we look at the units, then the unit of acceleration is L by t divided by t, which means it becomes equal to L by t square, and in SI units this will be meters per second square, or if we are talking of larger measurements, for example vehicular measurement, it could be kilometer per hour square. Now, the expression for these are the units for acceleration. Now, we can also define then instantaneous acceleration just as we defined the instantaneous velocity, and this will be equal to delta v by delta t in the limit delta t going to 0. So, and this is equal to, in terms of calculus, this will be equal to dv by dt. So, the instantaneous acceleration is the rate of change of velocity with time in the limit delta t goes to 0, and this is also the derivative of the velocity. Now, given the geometrical interpretation, we will realize that acceleration is the slope of the tangent of the Vt curve. Once again, this is a vector quantity acceleration, and this could be either positive acceleration is a vector, it could be positive, it could be negative, it could be 0. Now, sometimes the negative acceleration is also referred to as retardation, and if the term retardation is written, then it is, then the negative is assumed, that means the acceleration is decreasing with time. If we look at these accelerations in terms of our graphs, so an xt curve, if we have, if the curve for xt is upwards, this represents a positive acceleration. If we have the xt curve which is downwards, so that means in this part this is a downward curve, this represents negative acceleration. And what will happen if the xt curve is a straight line? If the xt curve is a straight line, that will give us that the velocity is constant, which will mean that acceleration is 0. So, if we have the xt curve like this, or xt curve which is in the shape of a straight line, xt curve implies 0 acceleration. Now, if we look at these relations between x and v in terms of in terms of calculus, in terms of derivatives, then what we have shown is that the way we describe velocity, now in further discussion the word instantaneous will not be used, because when we talk of velocity and acceleration, it will be assumed it is instantaneous velocity and instantaneous acceleration. Only when we want to talk of average velocity and average acceleration, we will use the word average, otherwise it will be kept as instantaneous. So, now what we have is, first we had x as a function of t, let us say, then we have dx by dt, this is what we define as the velocity. Now, because this is one dimensional motion, we are writing it like this, but in general case what we will do is, we will put a vector sign to represent these as vectors. I am not going to get into vectors for this part of the course, but when we go to later 2-dimensional and 3-dimensional motion, we have to use the vector signs. So, here what we have is, for 1-dimensional motion we write dx by dt is equal to v, and dv by dt, this is defined as acceleration, and therefore dv, since it is dx by dt, those who have some idea of differential calculus, this also becomes the second derivative of x with respect to time, because it is a d by dt of dx by dt. So, this is also written as d2x by dt square. If you know differential calculus, you will understand this. Otherwise, to understand this, you will have to see differential calculus. Now, let us see some interpretations of this. So, dx by dt is equal to v. Now, dx by dt, derivative of any quantity, represents the slope. So, when we look at, let us say if x is given as a function of t, then dx by dt is equal to v. So, that means in the xt curve, the slope gives you the velocity. Now, we try to invert this, and the way we invert this is, that means we assume everything is given to us here as a function of time. So, therefore, what we can do is we can write this as dx is equal to v dt. So, in some sense we are assuming either v is constant or given to us as a function of time. And here if we integrate this, then what we will get is, now integral dx is equal to integral v dt. So, if I have v versus t curve, the area under this vt curve, this area from t1 to t2, this area is represented by this integral, and integral dx will give me x2 minus x1. So, therefore, the area under the vt curve, this represents displacement. So, area under vt curve, this represents displacement. So, what we have seen is the slope of the xt curve gives us v, whereas the area under the vt curve gives us the displacement. Now, we can move ahead with the same thing with the acceleration. So, we have dv by dt is equal to a. So, here when we integrate, we will get integral dv is equal to integral a dt. So, once again now the slope of the vt curve gives acceleration, and the area under the acceleration and time curve gives the velocity, or in this case it will be the change in velocity between the two positions or the two times. So, now a sort of a slightly more complex situation arises if acceleration is known as a function of x. That means the acceleration which we have seen is dv by dt is given to us as a function of displacement, not as a function of time. So, therefore, in this case what we can do is, so we have dv by dt is equal to a. Now, what we can do is we can use the chain rule of differentiation, because acceleration is given as a function of x. So, what we do is the dv by dt, we want to write it in terms of x. So, this can be written as dv by dx times dx by dt, and dx by dt is velocity. So, this becomes v times dv by dx. And from the product rule of differentiation, what we also realize is that this is nothing but half times d by dx of v square. Once you know the differential formulas, these things will become very simple, but otherwise if you do not understand that, just look at it. What is the d by dx of v square? That is 2v times dv by dx. 2 and the half cancel and we get v times dv by dx. So, therefore, because acceleration is known as a function of x, we write dv by dt as v dv by dx, or half of d by dx of v square. So, therefore, what we get is half d by dx of v square is equal to a, and we take a on the other side. So, we get half of d of v square is equal to a dx, and when we integrate both sides, so we will be able to get the left hand side will become half of v square from position 1 to position 2 will be equal to the integral of a dx, and this will becomes half of v2 square minus v1 square is the integral of acceleration with respect to x. Now, this is, we have to resort to this if acceleration is known as a function of x, or we want to express acceleration as a function of x, because you realize there is a play of 3 variables x, t and a here. So, and v, there are basically 4 variables, and we have the relations if x is known, derivatives of x with time is velocity, and second derivative or derivative of velocity with respect to time is acceleration. And here by doing this we are trying to represent how acceleration is related with x, or how we find velocity as a function of x given acceleration as a function of x. Now, we may realize, some of you who have seen some mechanics, we have a principle of work energy, where we say the change in kinetic energy is equal to the work done by forces. And this relation which I have derived here is actually what plays a role when we talk of change in kinetic energy, because here if you look at it, if I multiply both sides by mass, I am not introduced these concepts, I realize, but some of you may know what is kinetic energy and what is work done. So, for them you can appreciate this, others will appreciate once we come to the definition of kinetic energy. But here if I multiply both sides by mass, then the left hand side becomes half m v2 square minus v1 square, which becomes the change in kinetic energy. And if I multiply the right hand side by mass, it becomes ma dx. Ma, for those who have seen, comes in Newton's laws term, is the second law of Newton's law tells us is equal to the sum of external forces. And when you take an integral of f with respect to x for straight line motion, this gives us, this is what we will define, force times displacement we will define as the work done. So, therefore, the work done becomes equal to change in kinetic energy, essentially is a relation which in some sense can be seen as following from here. So, here we have seen the general relations of v and x. Now, there is a very special case which we call case of uniform acceleration. Now, uniform acceleration means that acceleration is constant. In general, acceleration itself could change with time, but the formulas derived now will be for the special case when acceleration is constant. And the reason why this case becomes of practical importance is that when a body is falling under the influence of gravity, then there the acceleration for that body, if no other force is acting, is constant, and therefore it becomes a very common situation. In sometimes when we apply, when the car is moving, it could move with a constant acceleration. Sometimes when even when it does not move with constant acceleration, if it is almost constant, we assume it to be constant and apply the formulas which we get for motion of a car. So, therefore, practically this becomes an important situation, and for case of free falling, a body freely falling near the surface of the earth, acceleration can be treated to be constant, which we call as the acceleration due to gravity. So, here what we will do is we will derive relations between the displacement x, the time taken t, and initial velocity v0 a final velocity v and acceleration. That means what we are assuming is there is a particle which at time t is equal to 0 has a velocity v0. It is undergoing uniform acceleration, that means, and after a time interval t, its velocity is v and the displacement which has undergone in this interval is x, and acceleration during this whole interval is equal to a, and it is constant. That is the point which the most errors which people make is when acceleration is varying with time, if you use the formulas derived now, they will not work. They work only when acceleration is constant. So, for constant acceleration, what we realize is the acceleration will, because this is not changing, so that will be equal to v minus v0 divided by the time interval. So, acceleration can be written as v minus v0 divided by t, and this gives us v is equal to v0 plus at. So, we can think of this as the first formula, that velocity at a later time will be given at the initial as the initial velocity plus the uniform acceleration multiplied by the time interval. So, if we look at this now as a curve under the Vt curve, the velocity at time t is equal to 0 is v0, and at a later time at time t is equal to t, this velocity, so this is v0 here, at time t is equal to t, the velocity is v. So, now what is the displacement in this interval? The displacement which we know will be the area under the Vt curve. So, if we calculate this area, what we realize is this is v0t. So, the area of this rectangle is v0t. This is v0. So, this height is v minus v0. This is t. So, this area of the triangle, this will be equal to half times v minus v0 times t. So, the total area, this is equal to v0t plus half times v minus v0t, and v minus v0 from here we can write it as at. So, this becomes half at square, and this is equal to v0t. So, therefore, this area which is the displacement, so the displacement is given by v0t plus half at square. So, we can write it as x is equal to v0t plus half at square. If we expand this formula, that means we do not express things in terms of acceleration here, then what we will get is x is equal to v plus v0 by 2 times t. Now, if we want to know velocity in terms of a and x, that means we want to eliminate time, then what we can do is, time we know is v minus v0 divided by a here. So, we can write x as equal to v plus v0 by 2 times t, which is equal to v minus v0 by a, and when we do this we get x is equal to v square minus v0 square divided by 2a, and this gives us v square is equal to v0 square plus 2ax. So, these we can take as the basic formulas. So, if I just list them again for sake of completeness, what we have is the first formula, which was v is equal to v0 plus at, and then we had x is equal to v0t plus half at square, and then we have v square is equal to v0 square plus 2ax. Now, once again we should keep in mind these are not sacrosanct formulas, they are valid only if A is equal to constant. Now, in the above formulas we realize x is the displacement. Now, we could have a case where x 0 is not 0. So, in these formulas, in above formula, x 0 has been assumed to be equal to 0. If x 0 is not equal to 0, then x will be replaced by x minus x 0, because that is what the displacement will be. So, if you choose a reference such that the initial displacement is not 0, then x is here will be replaced by x minus x 0. So, now when it comes to application of problems, you have to see which quantity is given and which is not given. For example, in this formula, x minus x 0 or the displacement is missing. So, if you are given v and a and you have to find t, so then x minus x 0 does not occur anywhere in the problem. You use this formula directly to get a relation between v, v 0, a and t. Similarly, when we look at this formula, in this formula the final velocity v is not there. It tells you a relation between the displacement v 0, a and t. In this formula, when we see here, t is missing, t is not there. So, if t is not there, then we use this formula. And so, therefore, depending on what is given in the problem, what is asked for, you have to look at this. And then there is one more catch about which we have to be careful, and that is the sign of A, because in all these formulas we have plus 2ax or half at square. So, if we have, if acceleration, if in velocity increasing in direction of positive x, then A is positive, and which is what we call as acceleration. But if velocity is decreasing in the direction of positive x, then acceleration is negative, and as we said, sometimes this is also referred to as retardation. So, then because there are some formulas where you have minus half at square. For example, one has to be careful when we use this formula x minus x 0 is equal to v t, we have plus half at square, but if acceleration is negative, then you put a with a negative sign and it may become v t minus half at square for negative acceleration. So, these things have to be kept in mind. Now, as we discussed, one particular case where formulas, where this constant acceleration is very often used is the case of free fall. Free fall means a body falling under the influence of gravity near Earth's surface. As long as the body is not very far from the Earth's surface, then the acceleration on such a body is constant, and this is given by a constant which we use a symbol g, and this will be from the body, the direction of acceleration is from the body towards the surface of Earth. Now, for Earth, what on earth what we can find is, or what we observe is, the value of g is 9.81 meters per second square. For problems which we will solve, sometimes this value will be given, we either take it as 9.8 meters per second square, or for simplification sometimes if it is given to you, you could even take it as 10 meters per second square. This should be specified which value of g to be used. But what we talked about, the sign, is something which is very important. Let us say we talk of a ball which is thrown up, and so we throw it with some velocity, the ball goes up, and what will happen is eventually, because if this is moving up like this is the surface of earth, let us say from a window we are throwing this is earth. So because acceleration of this ball will be from ball towards the earth, that means it is in the downward direction. So if the ball is thrown upwards with a velocity v0, it experiences a negative acceleration. So therefore this velocity will start to come down, and eventually a point will come where this velocity will become 0. At that point what will happen is, this ball will start now, because its velocity is 0, it only experiences the acceleration due to gravity. So then it will start to fall down, and it starts to fall down till it hits the surface of the earth. So now here you have to choose the sign of the distance. So for example, if somebody chooses this as positive y, now whatever we have been calling as x becomes y here, because that is the direction of motion. So if somebody chooses y as positive upwards, so in this case, because your y is like this, then acceleration for free fall will now be minus g, and negative signs now will represent a direction which is downward. So here negative sign represents a downward direction, and a positive sign represents an upward direction. So if you solve a problem, you get the value of y or the displacement as positive, that means the final value is, the body is at a higher location than from where it started. Whereas if y is negative in an answer, that means the location is lower than from where it started. Okay. And now for the same problem, another student can do the same problem taking y downwards. Now if you choose y as downwards, then the acceleration will now be plus g, because it is in the direction of motion. And here now if you get a positive answer for displacement, that means you are at a lower position than where you started with. So now in the next class we will continue from here, and we will take up some examples of free fall and examples of constant acceleration, and we will also wind up this discussion on the equations of motion by studying relative velocity and relative acceleration, and solve problems of those types.